2 days before the ground gave way, geologists had walked directly across the patch of earth that would soon turn into a boiling gray wound in Yellowstone. They stepped over it, studied the basin around it, and left without seeing anything that looked remotely dramatic. No smoking crater. No collapsing rim, no warning sign obvious enough to stop a person in their tracks and say, "Do not stand here." Then, in the early morning darkness, that same stretch of ground ruptured. Hot water surged out, steam burst upward, sediment washed downhill into the Firehole River. And within days, the area looked like a place that had been quietly rewritten from underneath. That alone would be enough to make the headline feel unsettling. But the detail that makes this story more interesting, and honestly more unnerving, is that the phrase giant sinkhole is not really the right description at all. The thing that opened at Yellowstone is both less familiar and, in this setting, more revealing than an ordinary sinkhole. And the more precisely you describe what happened, the more disturbing the real story becomes. So let's clear up the first misconception immediately, because the terminology actually matters here. A true sinkhole, in the classic geologic sense, usually forms where groundwater slowly dissolves rock like limestone underground, creating an empty cavity that eventually can't support the weight above it. The surface then collapses into that void. That is the mechanism behind the famous sinkholes people associate with parts of Florida, Kentucky, or karst landscapes around the world. Yellowstone is dealing with a different machine entirely. What happened here is tied to hydrothermal activity, meaning hot water, steam, mineral sealing, underground pressure, and a shallow plumbing system that can reorganize itself with very little warning. The new opening near Black Diamond Pool in Biscuit Basin appears to have formed not because rock was dissolved away like a suburban sinkhole, but because a hydrothermal explosion fractured the area first, and then a new boiling pool formed through collapse in the unstable ground that followed. That distinction is not just technical hair-splitting. It changes what kind of danger this is, what kind of warning signs might exist, and what scientists are now urgently trying to learn from it. And the timeline here matters because, once you lay it out step by step, the event becomes much stranger than a single dramatic burst. Just after 5:09 in the morning on June 13th, monitoring instruments in Biscuit Basin picked up anomalous activity. There was seismic energy. There was infrasound, a low-frequency acoustic pulse human ears cannot hear. The first obvious suspicion was Black Diamond Pool, because that thermal feature had already produced a spectacular hydrothermal explosion in July of 2024, one that blasted water, rock, and debris into the air and destroyed part of the boardwalk. Biscuit Basin had remained closed ever since. So when the instruments reacted again in June of 2026, the easy assumption was that the same feature had erupted another time. But that theory started breaking apart almost immediately. The temperature record at Black Diamond Pool showed only a slight heat blip, nothing like the signature expected if the pool itself had violently erupted. And then the camera installed to watch the area captured the real source. At 5:09:50 that morning, a dark steam plume shot out of the ground north of Black Diamond Pool from terrain that had not been the main focus of attention. When Yellowstone geologists reached the scene the next day, they found 3 separate areas of newly formed vents a short distance north of Black Diamond Pool. Large amounts of hydrothermal water had poured from those fresh openings and run downhill into the Firehole River, turning the water a pale gray for kilometers downstream. One northern crack stretched about 18.5 meters long and up to 1.5 meters wide in places. It was still carrying water that measured around 90 degrees Celsius, almost at the local boiling temperature. Rocks had been thrown out around the fractured ground, but not especially far, which told scientists this was a relatively small explosion compared with the violent 2024 event. The middle vent group held several smaller vents that had already quieted into passive steaming by the next day, though temperatures still suggested very shallow boiling just beneath the surface. Farther south, closer to Black Diamond Pool, another broken linear vent had also sent water and sediment toward the river. In other words, the explosion did not create one clean cinematic crater. It cracked open multiple weak points and temporarily rerouted near-boiling water through a fresh network of openings. And then the part happened that makes the word sinkhole seem understandable, even if it is still not technically correct. When the geology team returned 2 days later, they found an entirely new pool of vigorously boiling, silty gray water near the middle vent group. Ground they had literally walked across had turned into a steaming basin between the evening of June 14th and the morning of June 16th. The pool measured about 6.5 by 5.3 meters, roughly 21 by 17 feet, and it was producing a thumping sound caused by steam bubbles forming and collapsing in the water. But the crucial detail was not its size or color, it was the missing debris field. There was no obvious ring of blasted material around this new opening, which is exactly why scientists concluded that this particular feature formed by collapse rather than by another explosion. The ground had not been violently thrown outward. It had caved inward into an already hot pressurized zone below, That is the point where the story stops being just a headline and starts feeling deeply unsettling, because an explosion, however dangerous, is at least a single release of energy you can imagine as an event. A collapse pool is a different kind of warning. It suggests the shallow ground had been weakened enough, hollowed enough, destabilized enough, that it could suddenly sag into the hydrothermal system beneath it after the first disturbance had already ended. And that means the surface can look ordinary until it simply doesn't. It means the danger is not only the instant of a blast, but the hidden process that keeps unfolding after the blast is over. In this case, the new pool did not merely sit there passively. By June 18th, camera footage showed it spouting water perhaps 20 to 30 feet into the air in intermittent, geyser-like bursts. Then on June 23rd, the same general area produced another hydrothermal explosion. So the real sequence was not one event, one hole, and then stability. It was an explosion, new vents, runoff into the river, a delayed collapse pool, active spouting from that pool, and then yet another explosion less than 2 weeks after the first one. That is the part of the story the headline is reaching for when it says experts fear it could grow. Not grow in the apocalyptic way social media likes to imply, not in the sense of Yellowstone suddenly tearing open into some continent-ending chasm, but grow in the very real and much more immediate sense that this unstable patch of thermal ground may continue evolving, finding new weak points, opening new vents, collapsing further, or reorganizing the shallow plumbing system underneath Biscuit Basin. And if you want to know whether that fear is justified, the answer is partly yes. The evidence from the past 2 years suggests this specific area has not settled down. Since the major July 2024 explosion at Black Diamond Pool, Biscuit Basin has remained unpredictable enough that park officials have kept it closed. That closure is not cosmetic. An entire famous thermal basin near Old Faithful has stayed off limits because the ground there cannot be trusted. To understand why the hazard behaves like this, you have to picture what Yellowstone's thermal basins look like below the surface. They are not giant open caves waiting to swallow people. They are more like tangled, shifting networks of cracks, fractures, and narrow channels through which hot water rises. That water is chemically active. It carries dissolved silica. As it moves upward and cools, silica can precipitate out and coat the walls of those channels with a hard mineral lining. Over time, that process can narrow pathways or seal them entirely. Imagine a vent that once let steam and hot water escape safely toward the surface getting slowly corked shut by its own mineral deposits. The flow beneath does not politely stop just because the outlet closes. Pressure starts building below. Temperature remains high. Water can become superheated under confinement. The system turns into a buried pressure vessel just a few feet under the crust people walk across. Eventually, one of several things can happen. The seal can fail suddenly and explosively, dropping pressure so fast that superheated water flashes into steam with violent force. That can blast rock, mud, and water outward in a hydrothermal explosion, or the ground above, fractured and weakened by heat and circulating water, can lose enough structural support that it collapses inward. Sometimes both processes become part of the same evolving episode, which appears to be exactly what made this Yellowstone event so fascinating to scientists and so unnerving to everyone else. The ground first erupted through several vent areas. Then, somewhere within that freshly disturbed zone, a new collapse pool formed. Then that pool started acting almost like a small geyser. In other words, the hazard did not conclude when the initial burst ended. The system kept changing in place. There is something especially unnerving about the fact that researchers had physically crossed the area before the collapse pool existed. Not because they made a mistake. They didn't. The basin had already been closed to the public, and part of the entire point of scientific monitoring is to document these changes. But it drives home how deceptive hydrothermal terrain can be. A person can stand over a section of ground that appears intact, while a completely different reality exists a few feet below. And unlike an ordinary volcanic eruption, which people imagine as molten rock forcing its way upward from deep underground, this kind of hazard is shallow, localized, and in some ways more immediate because it hides under terrain that looks deceptively walkable. The danger is not theatrical lava. It is near boiling water and steam under pressure beneath a mineral crust. Now here is where the story becomes genuinely important scientifically, because this event may offer one of the closest instrumented looks anyone has ever had at a hydrothermal explosion in Yellowstone. The June 13 event happened about 100 meters from a monitoring station installed in Biscuit Basin in 2025. That means seismic sensors, infrasound equipment, temperature data, and camera observations were all operating extremely close to the blast zone. That level of proximity matters enormously. A distant station might record only a smeared or faint signal. A nearby station can preserve timing, energy, and subtle changes in far sharper detail. Scientists now have a chance to examine not only the explosion itself, but the seconds, minutes, or perhaps hours leading up to it. And that brings us to the biggest unanswered question in this entire story. Was there any true precursor? any small seismic twitch, any faint acoustic signal, any thermal pattern, any tiny tell that the underground seal was about to fail. Because if the answer is yes, even in a limited way, it could become one of the most meaningful advances in forecasting hydrothermal explosions inside Yellowstone. Even a few minutes of warning would matter in a place visited by millions of people. But there is a more sobering possibility too. Scientists have been very open about it. The 2024 Biscuit Basin explosion showed no clear warning beforehand. If the 2026 data also reveal no reliable precursor, then the harder truth may be confirmed again, that some of these shallow steam-driven failures can occur essentially out of apparent calm. That possibility is exactly why the social media obsession with the Yellowstone supervolcano is so misplaced. Every time Yellowstone does anything dramatic, the internet rushes to the same conclusion. The supervolcano is waking up. The government is hiding the truth. New vents mean magma is rising. But none of that is what the evidence says here. The USGS volcano alert level remains normal. The aviation color code remains green. Monthly updates indicate background seismicity and no significant caldera uplift or subsidence during this period. There is no sign in these data that a giant magmatic eruption is building toward the surface. A hydrothermal explosion is not a baby version of a supereruption. It is a shallow steam event driven by groundwater, heat, pressure, and fragile hydrothermal plumbing near the surface. That should reassure people on one level, but it should not make the local hazard sound trivial. In fact, the reality is more grounded and more unsettling than the fantasy. The real danger is not a continent-ending eruption miles underground. It is that a specific corner of Yellowstone has spent 2 years demonstrating that the crust near Black Diamond Pool can fracture, vent, collapse, and boil over with very little notice. That is why Biscuit Basin is still closed. That is why the event matters. And that is why calling the new feature a sinkhole, while technically wrong, catches public attention. People instinctively understand the fear packed into the image of solid ground, suddenly becoming not solid ground anymore. There is also useful context in how often Yellowstone experiences this kind of activity. Small hydrothermal explosions are not unheard of there. Scientists have said events on roughly this scale happen somewhere in the park about once a year. Larger explosions that leave major craters are much rarer, measured in centuries rather than annual rhythms, and the truly enormous prehistoric hydrothermal blasts belong to a completely different timescale altogether. So measured purely by raw size, the June 2026 event was not the largest or most catastrophic example Yellowstone can produce. What makes it significant is the combination of repeated instability in the same basin, the formation of a collapse pool after the initial blast, and the unusually high-quality monitoring data captured nearby. There is even another recent Yellowstone example that helps frame the broader picture. In Norris Geyser Basin, geologists identified a new thermal feature in 2025 that seems to have formed gradually through multiple small events rather than one obvious blast. Satellite images suggested a depression appeared between late December 2024 and early January 2025, and by February, a blue water pool had formed. Infrasound data hinted at low-level activity, but there was no single unmistakable explosion signal. That matters because it shows Yellowstone's hydrothermal landscape does not change in only one dramatic way. Sometimes features appear through violent bursts. Sometimes they evolve in increments. Sometimes a zone that seems stable enough in one visit looks fundamentally different by the next. And that is really the honest meaning behind the fear that this Yellowstone opening could keep growing. Not that the entire park is about to rip apart, but that the local hydrothermal system in Biscuit Basin may not be finished adjusting. The new pool could stabilize, it could quiet down, it could remain roughly the same size and simply become another permanent feature in a basin full of dynamic ones. But it is also plausible, based on the behavior seen since the initial 2024 explosion and the continuing changes in June 2026, that the area could keep reorganizing. New cracks could open, existing vents could widen, small collapses could merge, more spouting or another modest explosion could occur within the same unstable patch. Scientists are not panicking about the end of the world. They are watching a volatile, shallow system that has already proven it can change quickly. If you want to keep your eye on what actually matters here, there are two things worth watching. The first is whether the close-range data from June 13 reveal any consistent warning signature before the explosion. That would be scientifically huge. It would not solve the problem overnight, but it could offer the first real foothold in understanding whether some hydrothermal blasts advertise themselves before they happen. The second is what this new collapse pool does next. Does it keep spouting? Does it expand? Does the surrounding ground crack further? Does the system calm down or keep reshaping itself? That behavior will tell researchers whether the local plumbing is settling into a new configuration or whether it is still actively searching for new escape routes. So no, this is not the Yellowstone supervolcano waking up. It is not the beginning of some cinematic mega disaster. But it is also not just a harmless curiosity or a mislabeled hole in the ground. A more accurate description is actually more disturbing than the viral headline. A hydrothermal explosion opened fresh vents in a closed thermal basin. Days later, a brand new boiling pool, formed by collapse in ground that had recently been walked on. That pool then started spouting on its own. Another explosion followed, and all of it happened in one of the most famous national parks on Earth, in terrain that used to look ordinary enough for tourists to cross on a boardwalk. The deeper lesson here is not that Yellowstone is about to destroy North America. It is that in places where heat, water, steam, rock, and mineral seals interact just below the surface, the most dangerous change may not announce itself with lava or earthquake swarms or a Hollywood skyline of ash. Sometimes it looks like nothing at all, until one morning the ground opens, the river turns gray, and a patch of earth that existed for who knows how long is suddenly gone. One more detail makes this entire episode harder to dismiss as a weird one-off. Biscuit Basin was not reopened after the 2024 explosion, and that matters. Park managers did not look at the damage, replace a little boardwalk, and wave people back in. They kept the whole area closed because the ground had shown it could fail unpredictably, and every new change since then has reinforced that judgment. In a place built around public access, scenic overlooks, and carefully managed boardwalk routes, a long closure is its own kind of statement. It means the people responsible for visitor safety do not believe this basin has returned to a trustworthy state. It means the danger is not theoretical. It is operationally real, and it is worth appreciating how local that danger can be. Black Diamond Pool itself was not the source of the June 13 event, even though it was the most obvious suspect. Other nearby thermal features were not dramatically transformed either. The instability was concentrated in a patch of ground just north of the famous pool, roughly 30 to 60 meters away, which is exactly the kind of detail that makes Yellowstone's hydrothermal system so deceptive. One zone can remain relatively unchanged, while another, just a short walk away, abruptly reorganizes. That patchiness is part of what makes forecasting so difficult. You are not watching one giant tank of pressure behave in a simple way. You are dealing with a cluttered, ever-shifting network of shallow channels where one blockage, one fracture, or one new escape route can redirect water and steam into a completely different point on the surface. There is also a psychological reason these stories spread so fast. People know what to do with a hurricane map or a wildfire perimeter. Those threats feel visible. Hydrothermal instability feels different because the hazard hides under beauty. Yellowstone trains visitors to look at vivid colors, steaming pools, and elegant geysers as attractions. Boardwalks create a sense that the landscape has been safely translated for human viewing, but the basin itself has no obligation to remain in the shape the boardwalk expected. The crust is not scenery first and geology second. It is geology first, scenery second, and sometimes the prettiest places are the ones changing most aggressively underneath. So the clearest way to say all of this is also the least dramatic. The opening at Yellowstone is not a classic sinkhole, and it is not evidence that a supereruption is around the corner. It is a collapse feature born inside an active hydrothermal disturbance, and it appeared only after an explosion had already fractured the surrounding ground. That makes the real lesson both narrower and more immediate than the viral version. Scientists are not bracing for the end of the park. They are confronting a smaller, nastier problem, a section of thermal terrain that may continue shifting without much warning in the exact kind of place where people normally expect the ground beneath a boardwalk to stay where it is. And when that expectation fails even once, every new plume, every gray runoff channel, every fresh crack, and every boiling pool becomes a reminder that Yellowstone does not need to erupt to become dangerous. Sometimes it only needs to keep changing.